So remove all lines that begin with the word today using sed. So here's a sample file. So here, I'll start it off for you. There's my contribution. So what kind of program could we use? What kind of sed program can we use to deal with lines that begin with the word today? You could substitute. So our general format is an address or a range of addresses and then some instruction. Where address somehow tells us what kind of lines we're looking for. So what could we use to try to pick up lines that begin with the word today? Regular expression, yeah. Shout that anytime that you say regular expression. People will be impressed. So let's look for lines that begin with today. So we start a regular expression with a slash. How do we specify a line starting with a particular word? Right? Put an anchor in the beginning, a caret, and then the thing we're looking for. We'll just say lowercase. Right? And that's all we need. We don't care what comes after today or if anything is there at all, but we want something that starts at the beginning of the line and has those 5 characters. So this is a pattern that matches any line that begins with today. And so our goal is to remove such lines. So how do we say delete a line from the output? Right, you can use the D instruction. And then you can list the file that you're trying to process. And that should probably do it. All right, so there's our original file on top. Here's the sed command. And we got rid of those 2 lines that started with today. So this works well. There's another way we could do this too. If we negate this condition, so this is saying delete any line that starts with today. The kind of dual to that would be print any line that doesn't start with today. So we could say, if it starts with today, not, go ahead and print. So any line that doesn't start with today, let's go ahead and print. And that will almost work. But it doubles most of our lines except the ones that begin with today. And this is where that -n switch comes in, because default behavior, read from input, copy to output. So every line appears on the output, and then if it doesn't begin with today, it appears again because we said print. So if we put in a -n, right, then we get what we wanted. So if we're negating it, we probably want, in this case, suppression of the default output. Okay, so flip that around, and let's copy only the lines that begin with today. So something like that. If the line begins with today, go ahead and print it, and we'll do the -n in the beginning to say don't do the default copying. right, so there's the lines that begin with today. And the counterpart to that would be, if it doesn't begin with today, go ahead and delete it. So you've got options. All right, how about removing all blank lines from your file? So we've got some blank lines in here. Well, we removed lines that began with today or didn't begin with today. So we can try to do the same thing. We just need a different regular expression. So what's a regular expression for a blank line? Yeah, just two anchors, beginning of the line followed by the end of the line. So if we match that pattern, delete, and there's no dash n, so it should copy every line. Except the blank ones. And that kind of worked. It got rid of that first line, that first set of blanks. But we've got some blanks in the next spot. So if you go into VI, you can say :set space list, and it will show you things like tabs and where the end of the lines are. This is throwing delimiters on for you, right? So we can see what's happening. Those two lines at the bottom aren't actually blank, they've got spaces in them. And we didn't tell it to get rid of things with spaces, we just said if the line's actually empty, get rid of it. So how could we modify this to also pick up things that contain blanks?
Beginning of the line followed by any number of spaces.
Yeah, so space, asterisk, $. This says match 0 or more consecutive spaces. So beginning of the line, any number of spaces, end of the line. And if we match that pattern, let's delete. So that should clean up the ones that aren't blank but aren't interesting. So space star, and there's your cleaned up file.
What if it was like mixed and spaces and tabs?
Then you got an issue. Right, so it's not going to pick that up. And so here I would probably make a script, said program, and I would probably do the following. Right, first change all your tabs to spaces, and then go ahead and substitute beginning space star $. And delete.
You also type it into a second set that one get all the.
Actually, yeah, that would be fine. Didn't like something in there. There we go. So \T for a tab. Cool. So these are puzzles, right? You got to do something like that, so you think about the things that you have in your toolkit and you try to find a way to piece them together. And it's if you like puzzles, right, Linux is a nice space to be. If you hate puzzles, well, then it's not so nice. But most programmers like puzzle solving to some degree. All right. change all cat to dog and adds a modification notice before the change line. Well, we already did something like this yesterday, right? So you can do an insert on a pattern, and then you can do a substitute. And that's not so interesting. Question 5, so write the first line, 5 lines into first and the remainder into last. Well, how do you pick up the first 5 lines? Right? So this says anything between lines 1 and 5 inclusive. And if we match that pattern, let's just write it into first. And then we could say 6 comma dollar and write that into the last. And hey, I've already got a file to do that. So let's make sure we're not cheating. Let's do a sed-n-fdiv foods. So that created a first and a last. There's the first 5, and there's the remainder. All right, so got an idea, right? Mess around with it. Think about those other exercises. Make up your own exercises, right? Just things that you can try to do with sed and with awk. It's usually good fodder for test questions. So play around with it and ask questions. So let's shift gears. Let's talk about system programming and processes and ways that we can interact with the Unix environment from C. Okay, so you can write a C program and you can think of yourself as just sort of inside a box, and you read inputs and you do processing and you print outputs, right? And that's fine. But it gets more interesting and more fun when you realize that your C program is not sitting inside a little closed off box. It's actually part of a Unix system. And you have access to everything on that Unix system from your C program. All of the commands that we can run from Linux, we can run from a C program. Right? All the things that we can do from Linux, we can do from inside our code. And that kind of expands the space of possibilities. So let's write some code. And when I was doing this last night, I needed all kinds of includes, and I don't know what comes from where, so I'm including everything. So some of you have already discovered the function called system, which you can use from inside a C program to execute a Unix command. So let's just say system date. And system will return an integer, so we'll print out the value of that return variable, and we'll just exit. So if you look at the manual page for system, it comes from level 3, chapter 3 of the manual pages. It needs to come from standard lib, and the calling is very straightforward. It takes a character pointer, that's a string, and it returns an integer. And we're not going to worry about this other stuff for the moment. right, so here's C1. So if we execute this, it says it's executing the system call, and then it shows us the date, which was the command that we sent to system, and then it says we're back from the system call, and the return value is 0. So that's a really quick and dirty way to execute a Unix command from inside a C program. And mostly I've seen people do this. So when you're writing a program and you want it to clear the screen, we can call a system command clear, and it clears the screen, right? So just like that. So we can start to explore what's going on here. So if we execute the command pwd, it tells us we're in home files 224 processes, which happens to be my directory. So it apparently runs your command from the current directory. Alright, so we can run an ls. And maybe we're in a goofy mood, so we decide to get into trouble. So we can run the command vi from inside our C program. And hey, it pops us into vi. And I can quit out of here. And when I exit vi, then it says back from the system call and shows me the return value of 0.
It would crash if you put it C1.
If you what?
If you built the system C1.
Yeah, that'll probably crash. So that's a version of what's called a fork bomb. Yeah. And that will probably crash. But we could do this. We could recompile our executable. And not much seems to have happened. But it did recompile it, right? It just changed it a moment ago. We could try deleting it. And that worked fine. But if we try to run it again, of course, it's been deleted. But why didn't it stop executing when we removed C1? How is it able to continue and say back from the system call?
It's already in memory.
It's already in memory, right? When we say C1, somehow bash reads the contents of that file, finds the binary code, the ones and zeros that the CPU is going to execute, loads them into memory, points the program counter to the first instruction, and it starts executing your code. Now, if C1 was very, very, very big and not all of it got loaded into memory, and it reached some point where it tried to find more of the program, it would find a problem at that point. But in general, small programs are already completely loaded into memory. So we can do pretty much, most reasonable things that we want to do. Now what if we do something that's not so reasonable? And our return code is non-zero. It's 32512. So why 32512? Is that a reasonable return value when we try to run the command ouch? Seems kind of weird. It's consistent, it's not random. So let's just say ouch, and we get an error. No, I did not mean touch. But if I echo this status variable, I see a 127. So how do we get from 127 to 32512? So 32512 divided by 127, hey, it's exactly 256. What's 256? quiz, $1 million. To the 8th. Disclaimer, there's no $1 million. So, this return value from system is 16 bits. And in this case, it was putting 127 up here and 0 down here. 127 was apparently the return code from our command. In this case, it was ouch. Well, let's push this a little bit. Let's just execute the command exit 11. And it comes back the return code of 2816. 2816 divided by 11 is 256. So we're on to a pretty good theory here. This is the return code from the command. This is if you're saying system cmd. And this is mostly a 0. And I think, don't quote me on this, but I think this is basically if something goes wrong with the call to system, you'll see an error code in this lower byte, like if it runs out of process space. And this is the return code from the actual command that you're executing. So you can take this and shift it right 8 spots, or you can divide by 256 and see the actual error code from the command that you're trying to execute. So you can play around with this. You can Google it too, but this is more fun, right? All right, well, let me go back to this. And let's take a closer look at the error message that we got. It was executing the system call, and then it said sh:1: ouch: not found. So what is sh? sh is a shell. If you do a man on sh, well, it brings up dash. But sh is another shell. Right, it's called the Bourne shell. So let's try this. Let's do a PS. And now we got something maybe unexpected. When we execute the PS command from system, we have two things happening. So let's do a PS -L. And let me make this bigger. So we've got bash. That's our interactive shell that we're sitting at here. That's process ID 541. C1 was the command that we executed when we typed C1. It has a parent process ID of 541. That's our bash process. So bash created a process called C1, and that had a process ID of 727. 727, that's the C1 process, is the parent of another process called sh. So C1 executed this command called sh. It started a Bourne shell whose ID was 728, and then 728, the Bourne shell, was the parent of another process, PS 729. So there's a whole hierarchy that took place here. We've got our Bourne shell, that's our normal interactive session. We typed C1, and the Bourne shell started a new process to execute C1. And when C1 got to the system call, it created a new process to execute sh, and then that sh process created a new process to execute PS. And PS executed, and we saw the output here, and then PS exited, sh exited, C1 printed its final message, and then C1 exited. And now if we do a PS, right, we've got the Bourne shell running, and we've got a PS that we just executed here, process 749, right? It's different from this one. So processes are being created and destroyed all the time. And this system call involves creating an instance of the shell and then using that to execute your command. So that's potentially useful to know. All right, so we can execute system commands. But those commands are just kind of running as part of the Unix environment. It might be useful if our C program could somehow grab the output from this date command so that we could execute a command and actually do something with it.
That's kind of what my question was going to be. Could you do system sed line 5 and then pipe that into a string? Or put that into a string?
You could. But unless you put that into a file or something, there's still no way to sort of pull that back into your C program. Right? We can put it into a variable. That variable is part of the shell, and once the shell exits, that variable's gone. Now we could use files, right? We could take date and we could redirect the output into a file, and then we could fopen the file and read in the information.
So basically, the system allows you to execute command line arguments, essentially.
Yeah, it allows you to execute basically any executable command in Linux. And you can send command line arguments along with it, right? Like ls-l or ps-l and so on. But it would be nice to be able to grab the output as well. All right, so let me see how far I got. All right, so So here's what we're going to use. We're going to use a system call called popen. And popen is kind of like system. It takes a string, which is the name of a command. It also takes an argument which can be read or write. Say if we want to read from or write to this command, and it returns a file pointer, just like fopen does. So if we fopen a file, we get back this file star that we can use with fgets or fprintf. Well, same thing with a popen, but with one major difference. So if we say popen, some command, and then a file type of W, right, just like fopen. Here's what happens. Command starts executing, and its standard input is redirected. And this file pointer basically feeds standard in of that command. So we say file fp equals popen some command comma quote w. We get back a file pointer, and anything we write into that file pointer gets forced into standard in of that command. Right, so it effectively creates it on the right side of a pipe. That's the P in popen. And this command is now running, but it's reading standard in from this file pointer. And if we open it with a quote R for reading, this basically executes command, but takes standard out and redirects that to this file pointer. So let's do some code. So I'll do a popen on date, and I'll open it for reading. I'll assign the output to fp, which is a file pointer. So we're back from popen, return equals, and let's just print out fp. It won't like printing it, but I'm not going to worry about the warning message. And we'll just use our standard read loop. We'll call fgets with that file pointer. We'll take 120 characters, store them in temp, and print out the value of that string as a %s, and we'll loop until fgets returns a null. And then when we're done, we'll close our file pointer just to be polite, and we'll exit. See how many errors I made. One error. Got an extra. All right, and the warnings because I'm printing a file pointer as a %d. I'm not worried about that. So let's go ahead and run this. So we'll run C2, and it executes the popen call. It comes back from popen, and my file pointer is some non-zero number. That's fine. And then it does an fgets on fp, and it loads that into temp, and temp is equal to, hey, it's equal to the date.
No, if the word file and all capital letters, can that be anything?
It's the file type. It's got to be uppercase FILE. So fopen is what we normally use, and it returns a pointer to this file type called uppercase file. So we've taken the output from this date command and we've captured it into a string, right, inside our C program. And we could do whatever we wanted with that. So this is a little better than system, right? System just runs and the output goes to standard out. Here the program runs, but the output comes back to us through this file pointer, and we can read it using fgets or fgetc. And do whatever we want with it. All right, so let's try with ls. All right, so each time we call fgets, it gives us another line of output from ls, which is another file name, with the standard new line sticking on the end, for better or worse. Right, so you want to know what's in your directory, you can use a popen, you can just use the ls command and have access to a list of all the files in your current directory. So that's a step in the right direction, right? It lets us grab output from a command. Let's go the other direction. So let's open the binary calculator program BC for writing. Let me start a new program. So let's open this for writing, and let's put some things in there. All right, so we're going to open BC with a P open. We're going to say we're opening it for writing. So we're doing this kind of thing. We're going to execute BC. It's going to read standard in from the other side of this file pointer. And when we write into this file pointer, that should feed standard in of the command, so it should act as if we had typed in these statements over here. And then we'll close the file pointer. Let me get rid of that, because that, no, I'll keep it in there. All right, so you ready? Here we go. So we can write to commands, we can read from commands. And that's pretty useful. What we can't do with this is write to and read from a command. Because when we do the P open, we have to say we're writing or we're reading. It's a pipe. And we can say which end of the pipe we're on, the input side or the output side. But we can't use this to say I want to send some stuff to a command and I also want to read the output of that command back in through a file pointer. So it's unidirectional, which is a little unfortunate, but not something we can't handle.
Unidirectional, not monodirectional?
I think either works.
Okay.
Depends on your interpretation. I'm thinking unidirectional as in one. I don't know. You might be right. All right, so let me tweak this a little bit. Let me go ahead and push those things out to the BC program, and then I'm going to say hit enter to finish and wait for the user to hit an enter. And then I'll go ahead and close the connection. And now when I run this, I don't see my output yet. Right? I opened the command, I printed those things in, and it says hit enter to finish. And then when I hit enter, I get all of my output. I honestly don't know if this will change anything or not. Yeah. So, so putting in an F flush, right, says go ahead and flush everything that I've written to this file descriptor. So remember, most things are buffered at the level of printf, fgets, fprintf. That's buffered I/O. Efficiency is the key. So fairly expensive to push an individual character out to the display or across a network or into a file. So every time you say print, your output doesn't go directly into where you're trying to print to. It goes into a temporary holding place called a buffer. And when that buffer gets filled up, and it'll hold, tens of thousands of bytes, when that buffer is filled up, then it dumps the whole buffer out in one fell swoop. Because that's a very efficient operation, right? Writing an individual character is very expensive because it takes a long time to start. But once you start, if you've got 10,000 characters to write, push them all out, that's very efficient. So normally, when you say fprintf and you're going into this end of the pipe, nothing actually gets sent to the command, right? We can force it to push things out by saying fflush and giving it a file descriptor. And so as soon as we call fflush, those things go to BC and it executes and it comes back and gives us the result. When we close a file descriptor, that forces a flush also. But if we want to force it to flush without closing, we can use fflush. But that can drive you crazy if you don't know that and you think this should be working and it's not. You can start questioning basics like 1 + 1 = 2 before you realize that it's buffering up your commands. All right. So let me talk about forks, because we got 5 minutes. I still want to talk about low-level I/O, but let's play with something more fun. So fork is a fairly harmless-looking command. Right, you run it and it doesn't seem to do anything, right? So I'm calling fork, and it returns an integer, and I run that and not much happens. So let me change this a little bit. So I'm going to print a message saying I'm ready to call fork, and then I'm going to call fork, and I'm going to save the return value in this variable r, and then I'm going to print a message saying I'm back from fork, and I'm going to print out the value of r. So what's the worst thing that could happen? You ready? Said ready to call, it called fork, and it printed back from fork twice. So what happened? What's the possible explanation for why this statement executed twice? If you know the answer, you can say it. There's no way to guess. The only reason that this statement would have executed twice was if this process was executing 2 times. Right? And this is exactly what fork does. Fork makes a clone of your current process. It creates an exact duplicate of your current process. And that duplicate continues to execute from that point forward along with the original code. So print ready to call fork happened once because we had one process when we said C4, and then the call to fork happens, but somewhere inside that call the current process gets cloned, and suddenly we've got 2 versions of C4 running. And so they both take the return value from fork, they store it in R, and they both execute this thing that says print back from fork, show me the value of R. And that clone is an exact copy with one difference, which is the return value from fork. One process will return a 0, the other process will return something non-zero. So these are the dots on the eyelet to know who's the clone and who's the original. Return from fork tells you. And if you get back a 0, you are the clone. Okay, what's called a child process. If you get back non-zero, you're the parent or the original. And the number you get back, that's the process ID of the clone. So right now we're up to process ID 21936. But when we ran this, 21926 was the next process to be created. That was the child process. Okay, so I've got a minute and a half to give you a really important disclaimer. Be very careful playing around with fork. Okay, so basic grade school denial of service attack is a fork bomb. If you call fork inside a loop, you will blow up your machine, If you do this on the Linux server, it should stop you from having too many processes, but don't bank on that, right? Because if you crash the machine while other people are in the middle of editing their code, they're not going to like you. But if you want to play with this on your own machine, especially if it's in a virtual box or something, right, you can have some fun with it. Fork is basically making a clone, and so here's something very simple we can do. Right? So we'll call fork 4 times. And when we run this, we get a whole bunch of output. Right? More than 4. Because basically the first call to fork created a child process that was a clone of the original. And now you've got 2 processes executing the second call to fork. And that creates 2 new processes, so now you have 4 processes executing the third call to fork, and you can see what's happening, right? So we're doubling the number of processes each time we call fork. So 4 calls to fork, not a big problem, right? But if you do this in some kind of uncontrolled way, you run out of process space pretty quickly. And your process gets errors on the call to fork, hopefully, or you run out of space and your machine crashes. So forks can be a little tricky to play with, right? So don't mess with them except on your own machine when you got backups. But we'll start from here tomorrow, and we'll play more with fork, and we'll start using fork to do something that lets us do two-way communication to commands we want to run. All right. So I'll see you tomorrow.